I have quite boring talk actually, because it will be just theory and a little bit of mathematics. But if you are like the mathematics, it may be not so boring. So I just warn you that you know what to expect. So yeah, I see that I'm already talking. So the talk is about oscillations of and stability of magnetized slender tori. In some sense, it's complementary talk to the first talk of this workshop of Maciek's talks, because I'm basically studying the same system, but our approaches are different. Maciek was talking about linear. Okay, both analyses are linear, but Maciek was talking about local analysis. I am talking about global analysis, but in order to be able to treat it, I make the system very small, so that these torus will be really kind of like a ring. And but still it's global, so it means that it inherits all these properties which global analysis should have, like taking into account the boundary conditions and so on. The other thing is, which is different, is that I will talk also about non-constant angular momentum tori. So these tori where angular momentum is not constant, but there could be some gradient. And I will show that these tori are actually unstable already in this very thin limit. So that is another complementary thing to Maciek's talk. Yeah, so the plan of the talk is like that. I am already done with introduction, and then I will talk about stationary solution. So basically the solution which I prepared, which is not mine, it's done by Commissaro some time ago. And then I will show you how to kind of simplify it in this limit to of very slender torus, and I will show that it has very simple structure, and therefore we are able to treat it analytically. Then I will talk about linear perturbations, but this section will be kind of more general than the rest of the talk, because here I need only the fact that I have some idea of fluid with the azimuthal magnetic field. So whatever I will say here is kind of a more general application. And then I will go to this special case of slender tori, and I will show you that they are governed by simple equation, which is of the second order. And I will talk about strongly magnetized tori and tori with constant beta parameter, which means that there is constant ratio of magnetic and gas pressure. And then at the end, I will talk about Parker instability in this tori. So the stationary solution. If you take this MHD equation in general relativity and do all kind of assumptions about symmetry, which means that we are assuming the stationary solution, so all time derivative goes away. Of course, metric is stationary and axisymmetry. If you assume that you are looking for the axisymmetric solution, then just by these symmetries, many equations are kind of satisfied trivially. And basically you end up only with single equation, which is actually poloidal component, which means the R and beta component of the Euler equation, and it looks like this. So basically, if I will put away this last term, it is just hydro, and we are kind of coming back to the old work of Marek and many others after. And but the magnetic field comes to this formula only by this term. And if you look at it, you will see that it's kind of very simple equation. So there is this U, which is effective potential of test particle, basically. Then there is some function that depend on the angular momentum distribution. So if there is in the torus angular momentum is constant, so this term goes away. Then there is pressure for, so I should say that this is kind of centrifugal plus gravitational force in the Newtonian. Okay, I will.
You have centrifugal ineffective potential, Ilka. Oh no, sorry.
Yeah.
Yes, you are right.
Yeah.
Okay,
so this is pressure force or thermodynamic force, and this is kind of this Lorentz force or this magnetic emission force. And yeah, so in general relativity, this angular momentum is defined by this this formula. Angular velocity is just the usual angular velocity, so the changing of azimuth in time, rate of change of azimuth in time. And then there is magnetic pressure, which is given just by this formula, and B is so-called magnetic force vector. We now are talking a lot about the meaning of this quantity, actually, and which is kind of, it is by definition assumed that it's measured in the reference frame of the fluid, so it's perpendicular to the pore velocity. And then there is this R square, which is given just by metric. And actually, if you go to infinity, you will find that only this term survives. This goes to -1, so it corresponds to the cylindrical R.
Ilka?
Yeah.
There is L square missing in the definition of the effective
Yeah,
potential.
there should be L square.
And that is why I said that you have centrifugal ineffective potential.
Okay.
Then I looked at this, I haven't noticed L square, and I thought it's a different potential, but it's a mistake, it's not a different potential.
Yeah,
There should be L square.
Yeah, there should be
in
L square here.
Yes.
I'm sorry. There will be
Okay.
many opportunities to correct
And then I'm
it.
not saying I'm sorry. I'm saying what I said.
Yeah.
You have centrifugal force in the effective potential already.
Okay, so we may discuss after. Okay, so basically you have this equation, which is still partial differential equation, and then the idea is to find at least a solution. So in fact, you may assume, for example, that if I would have the perfect fluid and barotropic fluid, then density and pressure is a function of each other. So all this pressure and the denominator is function of the same function. So you can express this as a gradient. If there is no magnetic field, this goes away, and then this term necessarily has to be also gradient. So from this you will derive that the angular momentum is just function of omega, or omega is just function of angular momentum. Their surface, they value surfaces coincide with each other, and they are coinciding with so-called von Seipel cylinders. So in the case of magnetic field, you may assume something similar, kind of to keep it as similar to the previous case as possible. So you may assume also that this function in the gradient is actually a function of the denominator. So you can express also this term as gradient, which is here, and then you basically have the same theory, or you could just inherit all the theory from the hydro case. So basically that is what Komisarov did, and actually he assumed the polytropic equation of state, and then some kind of polytropic equation of state for the magnetic field. So after these two assumptions, you can integrate it, because all terms are now gradients, and if you integrate it, you will get something like Bernoulli equation, which looks like this. So there are few terms. This term phi goes from this term with the angular momentum gradient, so it looks like this. Then there is this thermodynamic term, which gives you enthalpy, it looks like this. And then there is this kind of magnetic enthalpy, which looks like this. And of course, if you have polytropic equation of state, you can introduce so-called Lane-Emden function f, which gives you basically the pressure, density, enthalpy surfaces. And if you introduce it, you can express all these quantities in terms of just this Lane-Emden function like this. So actually there is one solution. The torus looks like this. So the thick line just corresponds to the surface of the torus, and then there were few points which are unfortunately invisible, but one of them is I think located somewhere here, and it corresponds to the maximal density and maximal pressure point. Then there is another which is a little bit to the right side, but just like a few centimeters, and it corresponds to the maximal magnetic pressure point. And the reason for this is actually the magnetic tension which arises from the curvature of the torus as it is surrounding the black hole. And this is the surface of the torus where all these quantities goes to zero, and then all these dashed line corresponds to the levels where the density or magnetic field takes its half of the maximal value. So you can see that magnetic field is kind of more concentrated to the center than the density. And this J actually corresponds to the synchrotron emissivity from this torus. So if this torus would emit synchrotron radiation, you will really see just the center of the torus. Okay, so you may do some algebra. So if you assume that you have very small sound speed, so the sound speed is now small parameter, much less than 1, and much less than the orbital speed of the flow, you may expand all these formulas in this small parameter, and you will get something like that. And you may expand also the two other, this effective potential and this potential which arises from the gradient of the angular momentum, and you will arrive actually at this. So this U and phi basically gives you this expansion, and I should say that here this x and y are some kind of local coordinates. So you can see that it's multiplied by metric, so it's kind of proper distance, but it's also divided by r0, so it's dimensionless in some sense. And in y direction or in vertical direction, it's basically the same. And so in these proper distances, this expression takes this form. And this omega r and omega theta are basically the second derivative of this effective potential u, and there are some factors from the metric, and these are called epicyclic frequencies. If you have just particle and which is moving around Keplerian circular orbit, and you just perturb it, then they will oscillate around this circular orbit with these frequencies. These are frequencies measured in the infinity, like distant observer. And then there is this kappa, which arises from this psi, so it somehow reflect the gradient of the angular momentum. So you can see that if angular momentum is constant, then because there is this derivative, kappa is equal 0, and basically you have just a radial epicyclic frequency here, and it's not visible here from just immediately, but I can just say that if you substitute the Keplerian angular momentum, you will find that kappa is precisely equal to radial epicyclic frequency, and therefore this term vanishes. And you have basically dependence only on the scale, on the height. So if you take this expansion and substitute to this Bernoulli equation, you will find such a simple equation. So on the left-hand side, there is this Lane-Emden function, which gives you how all these thermodynamics quantities and magnetic pressure behaves. And on the right-hand side, there is just function of the coordinates. And then there is this parameter beta, which is kind of some combination of the parameters of the torus, and you can see that when the speed of sound at the center of the torus is much smaller than the orbital speed of the flow at this point, then this parameter will be small. Therefore, this parameter multiplying, this constant multiplying this function will be big, and basically, so this, to balance this one here, this must be small, so you will end up with very small torus, which looks like ring, and which how is it called? Not the main circle, but the other circle to the main circle is much small, is a small parameter. And so if I am able just to solve this transcendental equation for f, I can kind of construct the arbitrary surface of arbitrary pressure and or density. So, for example, f equals 0 corresponds to the surface, f equal to 1 corresponds to the center of the torus, and so the surface of the torus is just solution of this equation when I put the 0 here, which means that this must be equal to beta square. Okay. So, but to kind of solve it, it's not easy because it's really a transcendental equation, and so there are some special cases. One case is when you have beta parameter infinite, which means that you are dominated by the gas pressure, and then you will get that this f is really equal to this function on the right-hand side. Then you have the opposite case when this equation has simple solution, and that is when this beta parameter goes to 0, so you are dominated by magnetic pressure. Then you have also another simple relation between these two functions, and then another simple case happened when mu is equal to this 1 plus 1 over n, and then you will get the same powers of f in these two terms, and you can solve it again easily, and this case corresponds to the constant beta parameter. So the magnetic pressure is always constant fraction of the gas pressure. Okay, so this is this system. And now about perturbations. So what I assume about flow is just that it's axisymmetric and stationary, and there is just azimuthal magnetic field. And what is really interesting is that even in such a general setup, all the equations get to the quite simple form, and that is why I'm including it here. So of course, if you have these two symmetries, then you can look for the solution in this form, which means that it depends on time and azimuth as sine or cosine or just harmonically. But then sometimes it is useful to define these other combinations like this tilt omega, which actually has simple physical meaning. It corresponds to the frequency of the perturbation as measured by the observer, which is co-moving with the fluid. And then there is another quite frequent combination, which is this M with tilt, and it is given just by this. And I have no idea what is its physical meaning, but probably there will be some because it appears very often. And then you just take all these equations and make the perturbation. So for example, from the four velocity normalization, because the four velocity in the stationary case have only time and azimuthal component, you will get simple relation between the time and azimuthal component of the perturbation. So for example, the covariant components are related by omega, contravariant components are related by angular momentum. Then you have the perpendicularity conditions, that this B has to be always perpendicular to the four velocity, and if you make the perturbation, you can find that all the time and phi component of the magnetic field can be expressed just as a combination of the pressure, magnetic pressure perturbation, and for velocity perturbation. So we have already two equations. Then the continuity equation gives you just particle number density perturbation in terms of the poloidal velocity perturbation. So if you write the continuity equation, you will end up with this simple equation, where this u is just, you see that is kind of, so it's poloidal velocity divided by the frequency measured in the comoving frame. So it's something like Lagrangian displacement or something like that. And so you have again quite simple equation and relation between these two quantities. What is quite surprising, that even the induction equation, which is usually quite complicated, simplifies in this case very much. And just if you take the poloidal component of this equation, you will end up with the simple relation between the poloidal component of the magnetic field perturbation and poloidal component of the four velocity perturbation. And if you project this induction equation onto the magnetic field, unperturbed magnetic field, you will get simple equation for the perturbation of the magnetic pressure, which looks like this. So this is kind of, for me, it was the most surprising. Such complicated equation could be simplified into this simpler form. Then if you project the Euler equation onto the magnetic field, you will get some combination of the time and phi component of the Euler equation. And it looks also quite simply. The only difference from the hydro case is appearance of this term, which actually appears already in the stationary solution. So it's also quite simple. And if you take the poloidal component of the Euler equation, it's also simplified quite strongly to this simple form. So it's just algebraic in this UK, and then there are all other quantities which I have already found from different equations. So I can, in principle, take all these, substitute to this poloidal equation, and I will end up with single equation for this velocity perturbation. And that I did, but I am showing it only for this idealized system of slender torus, right? So very thin or very slender torus. And the form of this equation is like this. So there is this sigma, which is some kind of eigenvalue. It's actually the frequency measured by the co-moving observer divided by ut, which kind of works as a redshift factor. So it's really a frequency measured by the distant observer. And then so this is the eigenvalue. This I is just a unit matrix. And then there is this operator L, which looks like this. It's quite complicated, but not so much complicated.
Could you go one slide back?
Yeah.
And then one line from the bottom. If there is no magnetic field, then this quantity would be this quantity W in the Papelovic-Pringle analysis, because it's of course.
No, not really, actually.
Not really.
I see. Yeah.
Okay.
It's really and this term here is really enthalpy perturbation, but in Papelovic-Pringle it's more complicated. But there is relation. So I have this this actually simple system which I have to solve, and I will quickly show you the solution. So for example, you can make the WKB analysis. Now I am going to the Maček direction, so I'm taking the local approach. And if I assume that the perturbations are of short wavelength, therefore the gradients of the gradients of the perturbations are much stronger than the gradients of the quantities characterizing the stationary flow or background flow. I end up with this simple equation, and if I assume the standard WKB approach to this, I will end up with dispersion relation, and it looks like this, so it's quite simple. And one can even identify with which waves are present here. And so when k goes to 0, you will find two solutions. One corresponds to this dispersion relation, and the other one corresponds to this dispersion relation. The first one corresponds to the so-called inertial waves. These are waves that are basically the main restoring force is gravity and the centrifugal force plus Coriolis force. This there is no pressure, no major pressure contribution, and the other one is just pure magnetosonic waves. So it's just actually it's fast magnetosonic wave. So there is this combination of the sound speed and half-length speed. And usually you can see that these are high frequency oscillations. These are low frequency oscillations because there is this k is just component, ky is just component of this k. So this is always less than 1, and this so this sigma is always smaller than this kappa square, and kappa square is 0 for constant angular momentum torus, and 1 or omega r for Keplerian angular momentum torus. So this sigma is always between these two bounds, and you see that these waves are actually absent in the case of constant angular momentum torus, which is actually quite important. Now I have just very short show about the main or the basic modes of this simple system, right? So in hydro, neglecting the magnetic field, Omer Bless actually found that these torus execute very simple motions. One corresponds to the radial epicyclic modes. So basically the torus is moving in and out with the radial epicyclic frequency. Then there is the vertical epicyclic mode. So again, this is doing like that. Then so these are modes that correspond basically to the motion of the test particle. The torus is moving as a whole in these two directions. And there are more complicated modes like this funny mode, which is X mode. And this mode actually corresponds to this inertial acoustic wave, inertial waves. And this X mode, if I am correct, I am maybe not actually. I don't know. No, this X mode is even present in the case of constant angular momentum torus. Then there is this plus mode, which is doing something like that. And so the plus is, of course, because when there is the maximal vertical exchange extent, then there is the minimal radial extent, right? And then there is breathing mode, when which is really kind of breathing torus. So when it is maximal in this direction, it's maximal also in this direction. So the volume is changing periodically. This X mode is actually radial, vertical, and X mode are incompressible modes. So the total volume of the torus is all the time the same, plus minus mode. Okay, no. Plus mode is so incompressible, and breathing mode is highly compressible. And of course there are more complicated modes, but these are kind of most simple modes that you can imagine. So our idea now is to see what will happen if there is some magnetic field. Will these modes survive even in magnetized media? And so we just first take into account the epicyclic modes, which means that this displacement vector is constant in the volume of the in the torus cross section, and then this operator which is in this eigenvalue problem simplified to this simple form, and you can find easily that there are two solutions that corresponds to radial displacement and vertical displacement, and the corresponding frequencies are your epicyclic frequencies. So it means that this mode is really kind of very robust, and it survives also in the magnetic field. And you can make the similar trick, and like here, just when the divergence of this displacement is equal to 0, which is exactly actually the condition of the incompressibility, and you will find that, for example, this X mode also survives. And I can say that this applies to all incompressible modes, which is quite reasonable, because if you have incompressibility, then you are not changing the pressure, and you are not changing even the magnetic pressure, and therefore your restoring force is not changed. Therefore, the eigenfrequencies are the same as in hydro. So this is not very interesting. Then, yeah, just here I am just saying that you can recover hydro if you put the magnetic pressure to 0, which is easy. Then you can study the oscillations of highly magnetized thorium, and then you are basically studying the eigenvalue problem with this operator. And then, but I will talk about this constant beta parameter torus, which is governed by this operator. And here I'm showing just how eigenfrequencies of these two compressible modes depends on magnetic field strength. So this 0 corresponds to the hydro case. This 1 here corresponds to the strongly magnetized torus. So here basically I have 0 magnetic pressure. Here I have 0 gas pressure. And you see that I am just showing the ratio of the frequencies of the breathing mode and vertical mode, and this was actually at some point quite strong candidate for high frequency QPOs, because it seems that this ratio is very robust. Okay, here it is. So maybe this corresponds to the hydro, I don't know. No, I'm a little bit confused. But you can see that this breathing and vertical mode are really very sensitive to the strength of the magnetic field, and this plus and radial are not very sensitive. And again, the reason for this is that the breathing mode are the most compressible mode, and therefore the magnetic pressure affect this mode very much. But plus and radial mode are kind of not so strongly affected by the magnetic field. And what was quite interesting that if you do the same procedure and look for the more complicated modes, you will find out that the modes which were stable in hydrodynamical case, and these modes actually corresponds to the torus with some radial gradient of the angular momentum. So these are basically inertial mode of this torus. So when there is magnetic field, then these tori could be unstable, and this pattern of these unstable modes look like this. Basically, these are the most simple unstable modes. So you can see that it's kind of vortices. So this is real instability. So there is zero real part of the frequencies. So they are just exponentially accelerating in this manner. So there are, of course, because of this symmetry, there are, of course, the radial version of this and vertical version of this. And you can, by simple analysis, because this work all the time is analytic, you can find easily the instability criteria. So just be warned that we are using Komisarov model very much, but actually in the case of non-constant angular momentum, they are very, they could be unstable for bad choice of the values of parameters. And they are unstable even in this case of very slender torus, and even in the case of low azimuthal wave numbers. So actually, this instability is much stronger than the Papalousian-Pringle instability or MRI in this case. And actually, if you make this just limit of the dispersion relation, which you find for no rotation, you will find that this instability criteria is reduced to this equation, which is actually the criterion for the Parker instability, and that is why we kind of identify with this Parker instability. But here you have rotating fluid, so it's more complicated. Yeah. Okay, I will skip this and leave you with conclusions. So this is just kind of laudatio for slender tori, that you can probe quite difficult physics or complicated dynamics, and still analytically by simple analytical calculations. So that is quite interesting. And of course, you may study even more complicated instabilities like Papalousian-Pringle or magnetorotational instability, but you need to go to bigger tori. So this is usually done by perturbative expansion in this small beta parameter, which gives you thickness of the torus. So if you kind of expand all equations in this beta and treat the beta as a small, you may study, at least in this limit, these two instabilities, but it's still far away. So that's it. Thank you.